From the job site to the code book, this is a Pool Envy podcast, where licensed pool professionals speak up. Code, compliance, craftsmanship. Hosted by Jason Davies, licensed across Wisconsin, Florida, and Texas. Your deep end starts now.
Welcome back to the Pool Envy podcast, where enough people have gotten bored with the idea of swimming pools that we're switching our topic to dentistry this week. Today, we're going to talk about your teeth. Yes, you heard that correctly, your teeth. And specifically, something called swimmer's calculus. And before anyone starts wondering why a swimming pool podcast has suddenly become a mathematics class, we're not talking about derivatives or integrals. We could go there, but that may end up creating some sort of tangent we don't want. See what I did? We're talking about dental calculus, tartar. There is actually a documented phenomenon involving frequent swimmers developing unusual deposits and staining on their teeth. But here's where it gets really interesting. Swimming pool water has also been associated with something that sounds like almost the exact opposite: dental erosion. In one situation, we're talking about material accumulating on teeth. In the other, we're talking about mineral being lost from teeth. How can swimming pool water be associated with both? Well, to understand that, we're going to have to talk about some chemistry, specifically pH, alkalinity, calcium, material equilibrium, and eventually we'll get to the Langelier saturation index, or LSI. And along the way, we're going to discover that your teeth and your swimming pool have more in common than you might expect. First, we need to understand what's actually on the surface of your teeth. Your teeth aren't sitting in your mouth as completely bare pieces of enamel. Shortly after a clean tooth surface is exposed to saliva, an extremely thin organic film begins developing on it. It's called the acquired enamel pellicle, or AEP. The acquired enamel pellicle contains numerous proteins and peptides derived primarily from saliva. Among those proteins, with names such as statherin, histatins, cystatins, lysozyme, and alpha-amylase. Now, I just threw 5 names at you that probably don't mean much unless you happen to work in biochemistry or dentistry. So let's give them some context. Statherin is a small salivary protein that interacts with the mineral surface of your teeth. Among other things, it helps keep calcium and phosphate dissolved in saliva and inhibits unwanted mineral precipitation. Histatins are a family of salivary proteins involved in the mouth's natural defenses. They are particularly well known for antimicrobial and antifungal activity. Cystatins are proteins that inhibit certain protein-degrading enzymes called cysteine proteases in the mouth. They're part of a protective chemistry occurring in saliva and at the oral surfaces. Lysozyme is both a protein and an enzyme, dual action. It's part of our innate immune system and can damage certain bacteria by breaking bonds within their cell walls. And alpha-amylase is another protein that also functions as an enzyme. It's one of those things that begins breaking down dietary starches before your food ever leaves your mouth. So this isn't just some meaningless coating of saliva sitting on your teeth. It's a remarkably active biological interface containing proteins involved in mineral regulation, antimicrobial defense, enzyme control, and digestion. And the pellicle isn't inherently bad. Quite the opposite. It performs important functions at the tooth surface and can actually help protect enamel from chemical attack. But one of those proteins is particularly interesting for today's discussion. It's statherin. Statherin helps regulate what happens with calcium and phosphate in saliva. Saliva can actually contain enough calcium and phosphate that mineral precipitation would otherwise be favorable, and proteins such as statherin help inhibit uncontrolled crystal growth. That's important because dental calculus is essentially a mineralization problem. Plaque accumulates on the tooth, and calcium-phosphate minerals can precipitate into it and harden it into what we call calculus, or tartar. So your mouth already contains its own remarkably complicated system involving pH, calcium, dissolved minerals, saturation, proteins, and mineral surfaces. Sound familiar? Because now we're going to put that entire system into a swimming pool. The surface of your tooth normally exists in an environment controlled largely by saliva. Saliva has a pH. It contains calcium. It contains phosphate. It contains proteins. It has buffering capacity. And all of those things continuously interact with the mineral surface of your teeth. Then you jump into a swimming pool. Now we've introduced an entirely different chemical environment. The swimming pool has its own pH, its own alkalinity, its own dissolved minerals, its own sanitizer chemistry, its own buffering system, and its own saturation conditions. For somebody who spends 20 minutes in a swimming pool a couple times during the summer, that exposure is one thing. But think about a competitive swimmer. Someone who may have spent hours in chemically treated swimming pool water day after day. That's a very different exposure. And researchers have documented substantially greater staining and calculus-like deposits among frequent competitive swimmers. This phenomenon is sometimes referred to as swimmer's calculus, swimmer's stain, or more broadly, swimmer's mouth. Exactly how every component of swimming pool chemistry contributes to that process is more complicated than simply saying chlorine causes tartar, and that's an important distinction. Swimming pool water isn't creating some mysterious new protein. The proteins were already there. The pellicle was already there. What changed? The chemical environment surrounding them. We've taken one mineral equilibrium system, your mouth, and repeatedly exposed it to another chemical system, the swimming pool. And researchers have observed the consequences. Now, let's talk about erosion. Tooth enamel consists predominantly of a mineral called hydroxyapatite. Hydroxyapatite contains calcium and phosphate. Under sufficiently acidic conditions, dissolution of that mineral becomes increasingly favorable. Mineral can leave the tooth surface. Over time, that can become dental erosion. And swimming pools have actually been investigated in documented cases involving significant enamel erosion among frequent swimmers. Some of those cases involved improperly maintained pools with extremely low pH. That's important because when people hear about swimming pool water damaging teeth, there's a tendency to immediately blame one thing: chlorine. But chemistry is rarely that simple. The better question is, what were the conditions of the water? What was the pH? What was the buffering capacity? What minerals were present? What was the saturation state? How long was the swimmer exposed? Because the pH number printed on your test kit isn't an isolated piece of information. It's part of a chemical system. And here's where the story becomes even more interesting. Researchers have also documented dental erosion in competitive swimmers exposed to pool water with a relatively neutral pH. The problem wasn't simply that somebody had created an extremely acidic swimming pool. The water was reported to be undersaturated with respect to hydroxyapatite, the mineral making up most of the enamel. Think about what that means. The pH by itself didn't tell the entire story. Mineral saturation mattered. Now, if you work with swimming pools, that concept should sound extremely familiar, because that brings us right back to swimming pool water. Swimming pool water contains dissolved inorganic carbon in several related forms. Carbon dioxide can dissolve into water. Through a series of equilibrium reactions, we can have carbonic acid, bicarbonate, and carbonate. These forms exist in equilibrium with one another. And one of the major things controlling their relative proportions is pH. At the pH we normally encounter in swimming pools, much of our carbonate alkalinity exists as bicarbonate. As pH rises, the relative amount of existing as carbonate increases. Why should we care about carbonate? Because our swimming pool contains something else: calcium. When sufficient calcium and carbonate are present under favorable conditions, calcium carbonate can precipitate. That's one way we get scale. Move the chemistry sufficiently in the other direction, and calcium carbonate containing materials become susceptible to dissolution. Think about materials inside a swimming pool: plaster, grout, mortar, cementitious finishes. These materials contain calcium-bearing mineral phases that continually interact with the water surrounding them. And now think back to your teeth. The chemistry isn't identical. I want to make that really clear. Tooth enamel is primarily hydroxyapatite. Swimming pool scale is commonly calcium carbonate. Dental calculus isn't simply swimming pool scale growing on your teeth either. Dental calculus consists primarily of calcium-phosphate mineral phases. Different minerals, different equilibrium systems, but they're illustrating an incredibly important common principle. Minerals don't exist independently of their chemical environment. Change the surrounding chemistry, and you can change whether a particular mineral system favors stability, precipitation, or dissolution. There's another swimming pool misconception worth clearing up here. pH and total alkalinity are related. They are not the same thing. pH describes hydrogen ion activity. Alkalinity describes water's capacity to neutralize acid. In most swimming pools, bicarbonate makes up a substantial portion of total alkalinity. That's why pH and alkalinity are constantly discussed together. But high alkalinity doesn't simply mean high pH. And knowing the pH doesn't tell us everything about alkalinity. They're interacting pieces of a larger chemical system. This matters because changing pH also changes the distribution of our carbonate species. As pH rises, more of the dissolved inorganic carbon exists in the carbonate form. And if we have calcium present, we've now changed the conditions affecting calcium carbonate saturation. So when somebody says the calcium is high, my next question isn't necessarily, how do we lower the calcium? My next question is, what does the rest of the water look like? Because calcium hardness alone doesn't tell us what that water is going to do. And that, folks, brings us to one of the most useful concepts in swimming pool water chemistry. The Langelier Saturation Index, or LSI. LSI is frequently explained using phrases like, the water is hungry for calcium, or the water wants calcium. Those phases can be useful shortcuts. But water doesn't want anything. There isn't a tiny calcium detector floating around inside your swimming pool deciding whether it's hungry. What we're really interested in is the water's saturation state with respect to calcium carbonate. LSI gives us a way to evaluate that condition using several characteristics of the water. pH matters, calcium hardness matters, carbonate alkalinity matters, temperature matters, total dissolved solids matter, and importantly, those variables interact. There's also a detail here that's worth mentioning. When cyanuric acid is present, it contributes to measured total alkalinity. So if we are interested in calcium carbonate saturation, we need to account for that contribution rather than blindly treating the entire measured alkalinity result as carbonate alkalinity. Again, it's a system. That's why a calcium hardness result by itself doesn't tell us whether the water is likely to deposit calcium carbonate or become aggressive towards calcium carbonate containing surfaces. And pH by itself doesn't tell us the entire story either. A swimming pool isn't 5 independent numbers written on a test sheet. It's one body of water undergoing chemical reaction. This is one of the reasons pH deserves so much attention. Changing pH doesn't merely move one number on your test kit. It changes chemical equilibria. With the carbonate system, changing pH changes the relative distribution of carbon dioxide, carbonic acid, bicarbonate, and carbonate. As pH increases, the proportion existing as carbonate increases. With calcium present, that can increase the tendency towards calcium carbonate precipitation when the water becomes sufficiently supersaturated. Scale becomes more likely. Move sufficiently in the opposite direction and conditions can favor dissolution of calcium carbonate. When we talk about balancing swimming pool water, we're not simply trying to make 5 independent numbers land inside 5 acceptable boxes. We're managing an interconnected chemical system, and that's an important limitation. LSI specifically addresses calcium carbonate saturation. It is not a universal measurement telling us whether the swimming pool water is good or bad. It doesn't directly predict every type of corrosion. It doesn't tell us everything about sanitizer effectiveness. It doesn't predict every swimming pool plaster problem, and it certainly doesn't calculate whether someone's tooth enamel is going to dissolve. Remember, hydroxyapatite and calcium carbonate are different mineral systems. And this is where those swimmers with dental erosion become such an interesting example. Researchers have documented dental erosion in swimmers exposed to water with relatively neutral pH that was nevertheless undersaturated with respect to hydroxyapatite. LSI wouldn't tell us that. It isn't supposed to. LSI describes calcium carbonate saturation. But the underlying lesson is incredibly valuable. The pH didn't look outrageous, and yet the saturation condition of the mineral still mattered. That's exactly why I don't like reducing swimming pool chemistry to a collection of acceptable ranges printed on the back of a test kit. A number can be in range, while the larger chemical system is telling us something else. Understanding what a measurement doesn't tell us can be every bit as important as understanding what it does. Apparently, quite a lot. Your teeth are a surprisingly interesting example of why the chemistry surrounding a mineral surface matters. Under sufficiently adverse conditions, swimming pool exposure has been associated with enamel erosion. Under other circumstances, frequent swimmers can develop characteristic deposits and staining associated with swimmers' calculus. Those phenomena aren't chemically identical to scaling or dissolution occurring in a swimming pool, but they remind us of something incredibly important. Water chemistry affects the materials that water touches. Now, consider the difference in exposure. A competitive swimmer might spend several hours a day in a swimming pool. The swimming pool itself spends 24 hours a day in the swimming pool. The plaster doesn't get out. The grout doesn't go take a shower. The heater doesn't towel itself off and go home. Those materials remain exposed continuously. When we evaluate a swimming pool, water chemistry isn't merely about whether the water looks clear. Clear water can still be chemically inappropriate water, and one acceptable test result today doesn't necessarily tell us what happened yesterday, last week, last month, or 6 months ago. Understanding the interaction between pH, alkalinity, calcium, temperature, dissolved solids, and saturation conditions gives us a much better picture of what may actually be happening inside that pool. Can swimming pool water affect your teeth? Yes. And depending on the conditions, researchers have documented effects at seemingly opposite ends of the spectrum. Mineral loss and mineral deposition. But the interesting part isn't the scary headline. The interesting part is the why. Your mouth is a dynamic chemical system. Your swimming pool is a dynamic chemical system. Your teeth contain calcium-phosphate mineral. Your swimming pool contains calcium carbonate chemistry. That's not the same equilibrium, but both teach us the same fundamental lesson. pH matters, buffering matters, mineral concentration matters, saturation matters, exposure time matters, and most importantly, chemistry has to be interpreted as a system. So the next time somebody tells you their swimming pool chemistry might be perfect because the water is crystal clear, remember, clear tells us what the water looks like. Chemistry tells us what the water is doing. And apparently, sometimes your dentist can tell too. I'm Jason Davies. Thanks for listening. Standards, not suggestions.
This podcast is for educational and informational purposes only. It is not legal advice, and it is not site-specific engineering, code, or safety determination. All field conditions should be evaluated in context. Thanks for listening to the Pool Envy Podcast, where licensed pool professionals speak up. Hosted by Jason Davies, licensed across Wisconsin, Florida, and Texas. For more insights, subscribe and join us next time.